Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Carol Stoker. Carol's going to talk to us today about her research on the Mars Phoenix lander. Carol did her PhD in astrogeophysics at the University of Colorado, and while still a PhD student, she organised the first Case for Mars conference, which eventually morphed into the Mars Underground and Mars Society, through which I personally became interested in Mars. So I have Carol to thank for my career path at the moment, and I'm sure I'm not alone in that regard. I first met Carol when she was organising the Mate experiment back in 2005. And she's been interested in robotic missions and drilling on Mars for quite some time now. Today she's going to talk to us, as I mentioned, about what she's found out about the Phoenix landing site. So if you'll all join me in welcoming Carol along.
Okay, I'd like to thank Adrian for inviting me to be part of this seminar series, which I've been intending myself. I think this is actually a great seminar series, probably the best one going on right now around town. What I'm going to talk to you about is the results of the Phoenix mission as they relate to an assessment of habitability. This was actually a goal of the mission, and the contents of this talk actually all come directly out of this paper, the Habitability of the Phoenix landing site, which is in the special issue of JGR Planets that is in press for the mission, but it is available online. And this is the the URL, or I guess the reference to get it online. Okay, so roadmap of the talk here. I'm going to start by presenting a formalism for determining the probability of habitability on a planetary surface. I'm going to review the Phoenix payload and mission results. I'm going to describe how the mission results were used to estimate factors that make up this habitability. And then I'm going to show the results for the Phoenix mission and for other missions, other sites where landed missions have occurred, and then I'm going to discuss the implications for future missions. Now, habitability, assessment of the habitability was in fact a key objective of the Phoenix mission. It says right in the proposal, the objective of the Phoenix mission is to search for a habitable environment. So what wasn't said in the proposal was, what does that mean? What is a habitable environment? Is it, fish swimming under the ground? The Phoenix mission organized the science team into 4 science theme groups, and one of those science theme groups was the biological potential science theme group, and I was asked to lead that theme group. And the first job I was given, in fact the only job I was given for the mission, was to figure out what was the definition of habitability and what could we quantitatively determine if Phoenix had in fact identified a habitable environment. So the working definition of a habitable environment is one that is capable of supporting living organisms with capabilities similar to terrestrial microbes. These conditions might be found in the present, the recent past, or the distant past. So in any of those cases, it would still be a habitable environment at the time that the conditions were met. Searching around after I was given this job, I realized that MEPAG had in fact done some work on this and had recommended a strategy for searching for life on Mars, which included a kind of a 2-phase approach. The first phase was to find environments that are or were habitable. And the second phase would then be to search for evidence of life consistent with where the environment, or the characteristics of the environment, so consistent with the habitable niche. Furthermore, MEPAG reports had stated that a life detection mission would be warranted only if the probability the environment was habitable was greater than 50%. This actually came out of an astrobiology field lab report, but other MEPAG reports have adopted a relatively consistent notion. So what I'm going to show you is a method for estimating the probability of a habitable environment as a number, a percentage. And this method was inspired in no small part by the Drake equation. In fact, when I really first got the job, I sat down and read the Drake equation and thought, now how could I apply this to coming up with a quantitative way to determine the habitability? Okay, so MEPAG, again, provided some guidance here. They identified 3 factors which control the potential for habitability in a specific time and space. The probability that liquid water has been present, the probability that there's an energy source available to biology, and the probability that the chemical building blocks of life are available. These factors must be present simultaneously, and so they suggested that a habitability index be defined, which is the product of these 3 probabilities. And you'll see that this starts to sound a lot like a Drake equation in the sense that you're estimating a product of a series of probabilities. Having worked through that logic, I realized that that's necessary but not sufficient. There's really additional information that needs to be taken into account, and that has to do with really just, is the environment benign and non-toxic? So in other words, these conditions could be met and the environment could still not be habitable. So I've included an additional term, which is this piece of B. Okay, so now that we've got the 4 probabilities, essentially what's done is that each of these 4 things are decomposed into contributing factors, and then the observations are used to evaluate each of those factors. And then the probability of each term is computed as a normalized sum of the factors, which are weighted relative to each other by the importance of the factor. And I'll talk a little bit later about how I did the weighting, but for the most part, that was a minor consideration. Typically, things were weighted equally. Okay, so there are, in fact, as with the Drake equation, there are problems with assigning values. So really, there's no way to assign an absolute value for any factor. All we can do is estimate the likelihood of anything being true from the observations. Furthermore, Phoenix did really not get all the measurements we need to evaluate all the factors. And things we did measure can often be interpreted more than one way. So given that, I used the following conventions to assign values to the factors. So basically, each factor was given a value from 0 to 1, corresponding to the following things. So if it was high, or given a value of 1, it was actually measured and the evidence was strong. If it was medium high, it was not quite as strong of evidence as it was for high. And the value was 0.75. If it was medium, it was measured, but there were many alternative interpretations, or the measurement was uncertain, or it wasn't measured, but there were strong theoretical arguments for a particular answer, and it was given a value of 0.5. So low was measured, but essentially a weak argument, or very uncertain measurement, lots of possible interpretations, and a low value. And then null, it was given only if it was looked for but not observed, or there was a good argument that it should, there was no good argument it should be there. Okay, let's go on to the mission description. So this is a picture of the Phoenix lander with the payload. The payload is really, this is not a rover. Payload is really designed to dig under the ground, and it's got a digging arm, And in fact, in many ways, it's similar to the Viking lander from the 1970s, of course with different instruments. But the Viking lander also included a robotic arm and dug into the soil. Just to go in a little more detail about the instruments, there's a surface stereo imager. This is an imaging system that provides stereo images for making digital elevation models and panoramic imaging. It's also multispectral, which provides imaging for geologic context and also information about the mineralogy, and also can be used for getting atmospheric and dust and cloud properties. There's a robotic arm which is designed to sample the hard icy soils. There's a scraping blade on the front of a scoop. There's also a little drill on the back that will allow you to get into very hard materials, because ice basically can't be scraped, or not enough ice can be scraped. So there's a little drill, and the drill actually augers cuttings up into the scoop. Mounted on the robotic arm is an instrument called the Thermal and Electrical Conductivity Probe, which measures the relative humidity in the atmosphere and soil properties, including the temperature and the conductivity and other thermophysical properties of the soil. There's also a camera mounted on the arm. This is a robotic arm camera, which is most useful for imaging the contents of the scoop at high resolution. The deck also has a thermal and evolved gas analyzer. This is the instrument called TIGA. It basically accepts a soil sample into an oven, and that sample is heated to 1,000 degrees C, stepwise heated. Calorimetry then tracks the heat of the phase transitions and uses that to identify various minerals, and also gases given off are analyzed with a mass spectrometer. This can be used to measure the presence of water and other volatiles, such as the decomposition of organics. The TIGA is able to detect and characterize organic compounds to parts per billion sensitivity. It allows you to identify aqueous minerals such as carbonates, and it also, with the mass spec, can determine isotopic ratios of key elements. Next, there is a wet chemistry laboratory, and basically soil comes in to a chute there. Water's added to the soil, and there's after the water is added, the detector is ion selective electrode, so it looks for quantities of soluble ions, in particular sodium, potassium, calcium, nitrogen, chlorine, magnesium, and sulfate ions. It also measures the pH of the solution. In addition, there is a optical microscope. This is part of the mecha payload. The microscope has resolution down to 3 microns per pixel, and it also includes an atomic force microscope, which has 10 nanometer topographic resolution. The samples are actually dropped into these little buckets on this sample wheel, and then they're imaged in the sample wheel. Some of the buckets contain magnetic targets on their surfaces, so that magnetic properties can actually be determined by what particles stick into the buckets. There's also a LiDAR, an upward pointing LiDAR in MET station. The LiDAR characterizes particles in the atmosphere, and the MET station measures the pressure and temperature in the atmosphere. Okay, so Phoenix landed on Mars on May 25th, 2008 in the early northern summer and operated for 160 days. Now, this is a solar-powered mission, and it was at a very high northern latitude. In fact, this is the landing site here, region D, and it was near 70 degrees north, so basically north of the Arctic Circle. and it was chosen to have a high concentration of near-surface hydrogen. So the orbital measurements from the Odyssey gamma ray spectrometer, and that's what this picture here shows, is the concentration of hydrogen in the northern hemisphere as a color-coded number from 0 to 100%. And what you can see is that in this region D, there's more than 50% hydrogen in the surface. Now, the gamma ray spectrometer, in particular, the instrument is a neutron spectrometer. It's only sensitive to hydrogen, so you don't know it's ice. You don't know what phase it's in, but the most likely thing is that it's going to be ice. And the landing site was chosen to have in the area with the highest concentration of ice, and also in an area that had the thinnest overburdened soil. So basically, because the digging arm was going to dig down to the ice and then sample the ice, we wanted the thinnest amount of soil between us and the ice that we could tolerate. This picture here is a high-rise image of the landing site, and the landing site was actually in heavily patterned ground, polygonal terrain, and these polygons are about 10 meters across, and I don't know if you can see it from there, but inside these bigger polygons there are smaller polygons that are roughly 1 meter across.
Is that white residual ice in the ground?
It's actually CO2 frost in the polygon boundaries, but that's actually an interesting point that I'll get to here in a moment. So this blue boundary here, so this is a picture now, a panoramic image stitched together from the SSI of the ground after landing. And this blue boundary is more or less the reach area of the robotic arm. And these two blue boundary boxes are the places where samples were acquired and where most of the digging occurred. So there were two locations, and we had this convention on the mission that all the names on the surface, anything you were going to name, would have to be given the name from a fairy tale. So these names over here were Dodo and Goldilocks, and then as the trench widened, they got merged into Dodo Goldilocks, which isn't a very good name. But the idea here was that the original sampling strategy was to get the samples Goldilocks and the 3 bears. But after we dug in this area a little bit, we uncovered this white material. But what you'll notice is that only one of the samples that we actually acquired was from this Dodo area. And in fact, it was a surface sample. The other thing to notice, if you look down here, here's Dodo, and here's the other place that we dug, the trench, which ended up being called Snow White, which was a misnomer because it didn't have any white material in it. and I think that has caused a huge amount of confusion in the science community. But anyway, what happened is all the samples that we acquired we got from Snow White. But if you look at how they come out in terms of the polygonal structure, the Dodo Goldilocks is actually in a trough area of a polygon, and Snow White is in sort of a polygon center. The red here is the high area. So again, this is color-coded elevation. So red is high, blue is low. The Dodo over here is in a blue area, and this is more or less what the polygon structure looks like right at the landing site. So in fact, in our sort of 1.5 meter boundary area that we could dig in, we actually had polygon center and a polygon trough. And we chose to dig in the polygon center. So again, there's our 2 sites, and most of the samples come from the polygon center. So that's kind of an aside. It will come back up later, maybe. But let's go back to now. Here's how we use the data to estimate the probability of our various probabilities. So starting with the probability of liquid water. two key factors go into evaluating that probability. First of all, observations, and second of all, theoretical factors. So observations and have morphological or chemical evidence of liquid water, and that is our observational factor, and then the theoretical models show that liquid water is allowed. That's our theoretical factor. I'm going to talk about these separately, but basically a weighted sum of those two basic ideas go into estimating the probability of liquid water. And the way we evaluate them is completely different. So this is one of the things about the way I did the weighting for these two factors. I assigned a greater weight to observations than theory, and that's just my bias. I'm not a theorist. A theorist would probably have done it the other way. Okay, so here's the observational factors, which again are the weighted sum of three individual factors, which are the macroscopic terrain morphology suggests liquid processes. So that's the first one. And the second one is minerals or compounds are found that form only in liquid water. The third is microscopic grain morphology suggests liquid alteration of grains. It turns out that these criteria were actually defined in advance of the mission. So when we actually got to Mars, here is, again, the Goldilocks Trench. And it was dug first, so Sol 20, Sol 24. This is as we were digging it. And what we found as we were digging it was that white ice, things got knocked off by the digging process, pieces broke off and disappeared quickly. So this is between Sol 20 and Sol 24. These chunks that are in the bottom of the trench and blown up here, by Sol 24 they are gone. They're completely gone. They have left no residue. Subsequent to that, I mean, that alone was enough to convince some people that this had to be ice and it was sublimating after it got broken off. Subsequent to that, we acquired spectra with the SSI, so this is basically multispectral imaging, and looked for a water ice absorption feature which was visible in these white patches. It turns out that if you mix soil in with ice, and it will actually obscure that feature, that absorption feature, if there's only 5% soil. So we know that this is nearly pure ice in this white area. We also knew from digging further down that the ice was in essentially a lens, and as we dug further, we could see that it extended over in this direction, but it did not extend in this direction. So it was a chunk of ice. Okay, so why is this interesting from a point of view of liquid water? Well, if this were occurring in Antarctica, we would call this an ice segregation. And ice segregations form where freeze-thaw processes occur. Here's one example. This is the example of ice wedge polygons. And basically, what happens in an ice wedge polygon is you get a crack. It's just from thermal cracking. And then when you get a layer that thaws, some of the water leaks down into the crack. And then eventually that causes the crack to widen so that you can get actually huge amounts of big wedges of ice that occur over time. Very standard thing in periglacial terrain. This is right out of a book on periglacial terrain. So ice wedges are one kind of segregated ice that's consistent with where the white ice was found, in that the white ice was in a polygon trough region. However, try as I might, I could never convince the other members of the Phoenix team that this was what was causing it. In particular, David Fisher, who has a paper, had argued in 2005 that vapor deposited ice could form ice segregations. And others have suggested other explanations. So the point is that this is a plausible evidence of liquid processes, but not a certain one. And due to the uncertainty in the deposition process, we assigned this evidence a value of medium. Okay, next was mineralogical evidence of liquid water. And this is basically a calorimetry plot from the analysis of the sample called Wicked Witch, which was taken out of the Snow White Trench by the TIGA instrument. So basically, what happens is when you have a mineral that decomposes, it causes you have to add heat to get that mineral to decompose, and that shows up as a power draw on the instrument. So this peak here is thought to be due to the decomposition of calcium carbonate. It's showing up in the right place for that to be the explanation. And this is a figure from Bill Boynton's paper on science from the mission. I would say it was a special issue of Science, but it was only 4 papers, so that's only 4 papers in Science. So analyzing how much carbonate that represents, TIGA team estimates that they have 3 to 5% of calcium carbonate in the soil. Calcium carbonate is formed as a product of aqueous alteration. There's very little other ways to form it at any kind of reasonable concentration. However, a similar amount of carbonate has been reported as a component of Martian dust by the people doing mid-infrared spectroscopy, in particular Josh Banfield, led a paper that reported this, although it actually has been reported by others previously. So this is about the same amount that they're seeing in the Martian dust, so the carbonate source may in fact not be localized. So for that reason, again, we assign this factor to a medium. Okay, next is microscopy and evidence for liquid alteration of grains. And these images are kind of fuzzy. They were JPEG compressed. They're not, even though they're 3 microns per pixel, they are not the crispest images in the world. But nevertheless, we see quite systematically a population of what I would call knobbly grains in the MECA OM images. And the grains have reentrants. Reentrants are little things like this. And structures that suggest solution removal of more soluble components. There are alternative explanations. In particular, we had a reviewer on our paper who was really hot on that these were evidence of vesicular grains. The person who actually did the microscopy part of this paper is John Marshall, and he has a lot of experience with microscopy, and he says that these do not look like vesicles. In fact, if they were vesicles, what you should be seeing is little holes, not little reentrants. But we can't entirely rule out that there's another explanation for this other than solution weathering. So again, we assign this a medium. Okay, so that's the observational evidence. Turning to the theoretical evidence. The theoretical evidence actually requires a combination, a product of 3 factors. So it's one of these things that all 3 of these things must be present simultaneously in order for liquid water to occur. So that's why it's not a sum, it's a product. So the 3 factors are one relating to the temperature, and this is where climate models show that liquid water is possible. One is related to, now what I mean by liquid water is possible is that the temperature and pressure are above the triple point. So what I mean is thermodynamically possible. Now there's lots of places on Mars where liquid water could form in the sense that the temperature and pressure would allow it to form in the summer if you put a block of ice on the ground. But you have to put that block of ice on the ground. In other words, there has to be a source of water there. So that's the second term, which is this emplacement mechanism for water. So like snowfall or ground ice, there needs to be a source of the water molecules in order to form water if you have thermodynamic conditions that allow it. And then finally, is it stable? Now on current Mars, evaporation rates are high, very high. So at best, it's only quasi-stable. Okay, so let's turn to what the theoretical arguments say about these things. This is a plot of the insolation at the Phoenix landing site over the last 10 million years. So this is how strong is the sunlight? And this is where we are right now. It's about 240 watts per square meter in the summer. Now this is at summer solstice, right? So you got this high frequency variation. What's that about? Basically, this is what the Mars orbit, I mean, that's exaggerated, the artist's concept of what does the Mars orbit look like. So basically, the eccentricity of the Mars orbit is such that when you're at perihelion, you're actually a lot closer to the sun than when you're at aphelion. And right now, perihelion occurs in southern summer. But the longitude of perihelion precesses with a 50,000 year cycle. So when perihelion occurs in the north, the solar flux is 23% stronger than it is right now. And Richardson and Mishna, this is the reference in 2005 in a paper in JGR, modeled with a climate model and a general circulation model what the climate would look like with that higher solar flux. And what they find is that in the northern plains at the Phoenix landing site, you get pure liquid water forming, in other words, thermodynamic conditions that allow it to form 10 days per year. And that is as recently as 25,000 years ago. So that's the high frequency stuff. What about this lower frequency? That's basically the quasi-periodic variation of Mars obliquity, which varies up to 45 degrees. At high obliquity, which has happened as recently as 1 million years ago, the solar flux is up to 2.5 times the present value at the position of the Phoenix landing site. And again, from this modeling, it's shown that liquid water can form up to 100 days a year under those circumstances. So for that reason, we give the factor for temperature, is temperature high enough for liquid water to form, a high value. But it's referring to when conditions are nice, which occurs periodically. Okay, so now the third factor is the ability to emplace water. And this is a picture from the LiDAR on Phoenix. And basically this is aerosols in the atmosphere, and this is the height of the aerosols. And so over here you see cloud, and this is actually as a function of time, so the thing can't move, it's pointing straight up. So about 5 o'clock, you start getting particles falling out of the atmosphere. These are fall streaks. And in fact, this is what's called virga. And in Antarctica, virga turns out to be a very significant factor of the snowfall that falls in Antarctica. It actually falls as virga. So we're seeing on Sol 99 of the mission, LSS 122, we're seeing snow actually falling on the ground. Now the LiDAR cuts off at 2.5 kilometers, so it can't actually track it all the way to the ground. But what we do see, and this is a picture of the ground early in the morning on about that date. And what you see is frost, white stuff, ending up on the ground. So the Phoenix mission found evidence of snow and frost forming at current conditions. And so there is a source. There is a way to get water ice into the system, even under current conditions. And furthermore, you have ground ice at depths of only 3 to 5 centimeters. That's actually how deep it was where we dug. So there's sources of water, and we assign this value for emplacement factor as a high. And then finally, again, I mentioned that evaporation rates are very high on current Mars. So even if you get liquid water, it's not going to hang around for very long. So the factor for its stability is assigned a medium. Okay, so that sums up the water story. Let's go to the energy story. So again, energy is the probability of the presence of a biological energy source. And there are two factors to consider, the solar energy as a biological energy source and chemical energy. One is relevant only at the surface. So here's the factor for solar energy. The problem with solar energy is that there's a terrific amount of sterilizing ultraviolet radiation. And in fact, Andy Sugar has done experiments to show that in only a matter of few hours, like 5 hours of exposure to UV at the surface, you sterilize the surface. So there's no possibility of growth right at the surface. Unless you can get into a niche that's got semi-transparent grains that block the ultraviolet and emit the photosynthetically active radiation. Well, in the microscopic images from Phoenix, we actually see semi-transparent glassy particles. So it's plausible that some organisms could actually live underneath those kinds of grains and still get enough sunlight to do photosynthesis. So on that basis, I assigned this factor a high value. Chemical energy is another story here. And this was actually a major mission discovery. The wet chemistry laboratory discovered that the soil contains about 0.5% of an ion of chlorine called perchlorate. This is a ClO4. And it turns out that perchlorate is a really good chemical energy source for many, many species, or many, many genera, I guess, of bacteria. There's many chemoautotrophs that use perchlorate. In fact, so many that there's a huge biotechnology industry around using perchlorate actually as or using these organisms to clean up perchlorate contamination, because perchlorate is actually considered a contaminant in many soils in the American West. So the thing is that perchlorate is the oxidizing member of a redox couple. So in order to have a chemical energy source, you need to have both an electron donor and an electron acceptor. And perchlorate is in the electron acceptor half of the story. This list right here is a list of possible electron donors. And none of these things are probably very likely to be found on Mars, with the exception of iron in the reduced state. It turns out that Phoenix had the capability to measure iron in the reduced state in the wet chemistry laboratory, and it was not observed. We are not really sure why. It might have been that the soil pH is fairly high, and the solubility of iron is a function of pH and is more likely to be soluble at lower pH. But what we do see is we see these dark rounded grains that are magnetic. So they have magnetic properties, and again, this is a microscopic image. So it's a pretty good bet that there is reduced iron on Mars, and there is other spectroscopic evidence that globally reduced iron is abundant. So for those reasons, again, we assigned this chemical energy factor to a high. Next then is the chemistry, the building blocks of life. And so this is the famous Schnapps elements, CH, NO, P, and S. And the fact they have to be available, and they have to be available in a biologically available form. For each element, if it was measured or known to be present, we assigned it a high. If we thought it was in the global soil, we assigned it a medium. Phoenix provides direct information only for carbon, hydrogen, oxygen, and sulfur. There is, P has been measured in Meridiani and Gusev soils and is also abundant in SNCC meteorites, so it's inferred to be present. The element with the highest uncertainty is nitrogen. Now there's nitrogen in the atmosphere, but it's at a very, very low partial pressure, much lower than on Earth. On Earth, the atmosphere is 80% nitrogen. On Mars, there's a few millibars of nitrogen, but the problem is it is not known whether bacteria can fix nitrogen in these low partial pressures. So this is actually an important measurement that is needed, but we actually don't know it for anywhere on Mars. We can only hope it's there. So in fact, the only sensible thing to do with nitrogen is to leave it out of the equation because we have no information. Okay, so just going back to this, basically these are not discriminators. In other words, all the sites on Mars basically get exactly the same score. Benign environment now, getting to the last probability. Here there's 4 relevant factors. First of all is water activity. In other words, is the water activity in a range high enough for growth? This is assigned high because the only relevant salt is perchlorate. All the chlorine on Mars seems to be tied up in perchlorate, at least at the Phoenix site. It's only at a 0.5% concentration, so unless you only mix a very small amount of water with it, it's not going to result in very salty water. So water activity does not seem to be a problem. A factor for the pH. pH was measured by the Wickel at 7.7, and that is about the pH of seawater. So that's we know that lots of things like to grow at that pH, so that's assigned a high. Then there's a factor for organics. In fact, if organics are preserved in the environment, that's a good thing for life. This factor is assigned a low. Now, the thing about this measurement for organics is Phoenix did not detect organics. It was designed to detect organics, and it went to Mars to detect organics, but it did not see any organics. However, because of the perchlorate, as you heat the sample up that contains perchlorate and organics, there is a high likelihood that they would oxidize to CO2. And in fact, a low temperature CO2 release was seen by the TIGA instrument that could be due to the combustion of organics. A LPSC abstract last year from Doug Ming about this. So it is plausible that there are organics that we were unable to detect because of the perchlorate presence. So as a result of this uncertainty, we assigned this factor a low, but not a 0. Okay, and then finally, temperature enters into this benign environment story again. And it's not, is the temperature high enough to support liquid water, but rather, is the temperature high enough for biology to grow? Because as it turns out, biology grow at lower temperatures than the freezing point of water. Okay, so is this condition met? The low temperature limit of growth is actually 253 degrees Kelvin. And this is a plot of the temperature. Actually, what it is it's a model showing how the temperature decays with depth in the ground ice. And this is with the ground ice at this level. And no, this is at Mars. This is at Mars. And so these are boundary conditions, which are the measurement of the temperature at the surface taken by the TECP as a function of time. So that's what these different curves are. So the red is at midnight, and this was the temperature at the surface. And this is how it was projected to be decaying as a function of depth by this model. So basically what we see is that at midday, noon to 3 p.m., the temperatures are above this 253 degrees limit. However, at the surface at that time of day, what we actually observe by Phoenix is we see the soil more or less breathing water. So at night, when you see this, or early in the morning where you see snow and you see the humidity actually go up to saturation and you see frost forming on the ground, the soil is saturated. There is ice forming on the soil. But that is happening at these very low temperatures, way below a growth limit. In the day, the temperatures get up to high enough that growth could occur, but the water is long gone. By that time, the relative humidity is down around a couple of %. So, so basically, liquid is gone by the time you get the temperature high enough. So I think the bottom line is that today, the modern conditions of obliquity and the phase of perihelion and the solar flux of 240 watts per square meter, we're not getting warm enough for biology, for growth to occur. However, Aaron Zent did some modeling, it's a paper in Icarus in 2008, which showed that at high obliquity, again, this is like 2.5 times more insulation, the 258 degree Kelvin isotherm penetrates down to 75 degrees centimeters depth for many sols. So the temperatures, basically this whole curve shifts to the right, and including the minimum temperature at depth shifts to the right. So again, at higher insulation conditions, temperatures allowing growth are most likely occurring, and for that reason this factor is assigned a high. Okay, so this now plots, adding all these stories and factors and estimates together, what do you get for the individual probabilities, liquid water, energy, chemistry, and benign conditions, and then how do they sum? And the point of this slide is that in the combined probabilities, you reach the 50% number, you're above the 50% number defined by MEPAG as being the criteria, of which, if it were that habitable, it would warrant searching for life directly, a mission to search for life. Now, my number, which includes another term, so now you've got a product of 4 probabilities instead of 3, is coming down to a lower value. It's only coming down up to like 45%. But that's because, you know, you're multiplying multiple numbers that are all less than 1. So the more of those you do, the smaller your result is going to be. And I don't know if the MEPAG criteria is the right one, but certainly we meet it. Okay, so I think what's really maybe more instructive, though, is to look at how this habitability index and the probability for habitability compares with other landing sites, such as the Mars exploration rovers, Viking, Pathfinder, etc. Now, there are some caveats here. We're comparing sites that don't have similar measurements, and there's no relevant information for many of the factors at some of the sites because these missions did not carry the same payload as Phoenix did. So in these cases, that factor was left out of the computation for that site. So in some of the sites, for example, Pathfinder, almost none of the relevant measurements are actually made. So you're leaving out, what you're doing is essentially assigning a lot more value to the remaining measurements because the other things have been left out. But nevertheless, here's how it comes out. And if you really want to know how I did these estimates for all these other landing sites, you'll have to get it out of the paper because obviously I spent a lot of time on Phoenix and not quite so much time on these other sites. So if you think I'm waving my hand for Phoenix, then what I'm doing for the other sites is really scary. But, but in any case, here's how it comes out. And what you see again, the term for chemistry, everybody got the same score. So it's really down to this benign environment and liquid water. Meridiani, the evidence for liquid water is much stronger than the evidence for liquid water at the Phoenix site. I don't dispute that. However, the environment, by comparison, may not be so benign. The evidence is that it was very low pH environment and therefore potentially a very stressful environment. And there has been a paper that's claimed that the water activity was low enough that it would have prevented life. I personally don't buy that argument, but that's why Meridiani ends up getting a lower score. Gusev gets a higher score because it probably did not experience that low pH environment. Okay, so here's how, if you add up you multiply out the 4 terms, this is what you get. Again, this is the MEPAG, 3 terms, and this is mine with the 4 terms. And Phoenix is the clear winner. It is the most habitable environment we have been to by about a factor of 2. So let's go to my conclusions. Based on what we know, the Phoenix landing site is the most habitable zone of any location we've visited on Mars. But what is really more important to me is that the northern plains are habitable in modern times rather than during the Noachian. The Mars exploration rovers have visited sites that were habitable 4 billion years ago. Signatures of modern life, if it exists, are much more likely to be found than signatures of life that were deposited billions of years ago. So future missions to search for life should land in the region explored by Phoenix. QED. Okay, so I said I would say a little bit about what are those future missions. Turns out that some of the members of the Phoenix team, myself included, have been for several years now working on a mission we call Icebreaker as a follow-on to the Phoenix mission. And this is a CAD model of one of the concepts that is being studied. So it's part of a mission study. And the idea here is to fly some of the more useful elements of the Phoenix payload, but instead of using a robotic arm, use a drill. The story is, if you look back at this insulation history over the last 10 million years, you've had warm and cold periods. Some of those periods have been very warm. What you would like to do is get to ice that was deposited in one of those very warm periods. If there's a biological record, that's where that is likely to be. Now, I personally would like to drill a lot deeper than 1 meter, but the more cautious and conservative voices have been winning out because basically the mass of the drill goes up as the depth that you're drilling to. And the payload is already a very, very mass-intensive payload. So a 1 meter drill allows you to do it with 1 drill string and not have to add additional drill strings. And it reduces risk. So hopefully in 1 meter you can get to ice that has been experienced much warmer conditions than present. Another thing we would like to do with this mission is use a different instrument to perform organic analysis, an instrument that doesn't use combustion, so it doesn't heat the sample to 1,000 degrees. And the other thing we'd like to do is actually search for life. So this mission contains an instrument that uses an antibody-based microarray that actually can detect life, can detect compounds that are produced by living organisms. And that is where I'm going to stop. I'm actually right on time.
Thanks very much, Carol. If I can ask the first question, I was wondering what your feeling is on the extendability of the conditions at the Phoenix landing site. Do you think that the same levels of perchlorate are found widely in the North Pole and perhaps even in the South Pole as well? What's your feeling on that?
Perchlorate is more than likely a photochemically produced, and what's providing the chlorine is volcanic gases. And so I see no reason to think that it's confined to the northern regions or the North Pole, or that would be very surprising if it were. So I think it's pretty likely that you see about that amount of perchlorate everywhere on Mars. And in fact, the fact that it's so high, that the concentration is so high, might actually itself be an indicator that there isn't a whole lot of biology chewing it up, because biology would break it down.
I'm curious because you mentioned UV sterilization, but yet didn't include anything about UV or ionizing radiation in your piece of B term. It seems like that would knock the probabilities down quite a bit.
So well, there's a lot of ways you might try to put this story together. The ionizing radiation was sort of included in the energy term, but it would knock down the probabilities right at the surface. But I see your point, and I think it's valid. It could very well be included in that term, but it specifically relates to, the environment right at the surface.
Well,
The ionizing radiation is another interesting story, because it turns out that Mars does go through has these warm periods, but also has very cold periods, because the other end of the cycle is that the obliquity is very low, lower than at present, and the temperatures are much colder than now. And those periods can last up to hundreds of thousands of years. And so the issue is ionizing radiation sterilizing essentially all the life down to a certain depth. There has been a paper by Kaminik who looked at that. And so his estimate was that you basically need to get down to a depth of 1 meter to get below the depth that gets sterilized. So I think that's another argument for why you need at least 1 meter of drilling to get to places that you could plausibly find organisms that are alive.
but it also knocks out photosynthesis as a possible energy source.
Absolutely. So you got to have chemical energy.
Wanda Davis, NASA Ames. Great talk, Carol. Thank you. I wanted to ask you about nitrogen, which seems to be the showstopper. So you indicated there's a relevant amount that would be required. We don't see it on Mars. Has anyone done any laboratory results under Mars-like conditions that would indicate the minimum value we absolutely need based on life on Earth?
I didn't say we don't see nitrogen. What I meant to say was we have not measured nitrogen. We have not attempted to measure nitrogen.
Thank you.
Now, WICL was actually designed to measure nitrate. And nobody thought that perchlorate would be an ion likely to be on Mars. And it turns out that the ion selective electrode that was included for nitrate is blown away by perchlorate. So it is actually, hundreds of times more sensitive to perchlorate than to nitrate. So it was saturated.
I see.
And So there's no information about nitrate. Now, there's some reason to believe there should be nitrate because in the Atacama, where perchlorate is enriched very, very much up to almost 0.5%, as much as we see on Mars, it's actually in these huge nitrate beds.
Yes.
And so there's a correlation, and they're both supposed to be photochemical products. So photochemistry in the Mars atmosphere could well have made, essentially all the nitrogen in the atmosphere into nitrate. And there could be a huge amount of nitrate in the soil. We just haven't measured it.
Thank you.
Hi, Carol. Couple questions. Was the ice that you found on Dodo Goldilocks, was that found on the smaller polygons or the larger trough polygons where high-rise saw the CO2 frost?
It was the smaller inner. Yeah, there is a bigger polygon, a big crack that runs. You can actually see in the Phoenix images, but it's not accessible to the robotic arm. So it was in the smaller inner polygons.
Okay, and then one other question. Do you recall what time of day and season that image was taken where they saw the water ice and it disappeared?
Yeah, it was the water ice that was knocked off by the digging arm was seen on Sol 20. So that was, I'd have to go back and figure out how that relates to El Cebes, but it was early summer because it was near the beginning of the mission. That is subsurface, so it was under it turned out it was under 3 centimeters of soil, whereas the other center of the polygon, there was no ice, pure ice there. There was ice cemented ground, so soil saturated with ice. Where all the samples were acquired was in the place that there was soil saturated with ice but no segregated ice. And why that occurred all had to do with the fact that the trough area was at a slightly awkward angle for the robotic arm to actually get in there and get sample. And that combined with the fact that the samples we did get tended to stick in the scoop and stick on the instrument and didn't pour into the instrument, and we were having all these problems getting samples into the instrument. And for those reasons, there was resistance from the engineers to trying to get samples from the white stuff. That there was a feeling that it would be both difficult to get them because of the awkward angle and that they would stick in the scoop or stick to the instruments.
And do you recall, like, what time of day? Was it early morning, late afternoon? I'm just kind of curious whether that water ice would have stayed around all day or it just would have...
No, the white stuff, once
evaporated.
We uncovered it, it was a block of ice. And it stayed around day after day after day. I mean, for 90 sols. Eventually, it disappeared, actually. But it didn't sublimate. Some of it sublimated, the surface of it sublimated, and there was enough soil embedded in it that as it sublimated, it eventually formed a lag deposit on its surface. And we did, in fact, scrape up the lag deposit and sample that with the microscope. So we looked at the lag deposit, at least we have microscopic images of the lag deposit that formed. But once you scrape that away, there was still white ice underneath it. So there was a thickness of ice, we don't know how thick, but.
So I like your idea for icebreaker, but my question is, why would you build it in the image of Phoenix?
That's a good question. It's really one of so when you do a mission study, usually you're doing it in response to a particular opportunity. At least the mission studies that we've done have been in responses to possible opportunities for flight. And it has been a paradigm in the space development world that if you have built something like that before, it would be lower risk and lower cost to build another one like that again. I personally question that logic, but that's been the logic driving it.
Yeah, because I think if I were going to rebuild it, I'd at least tilt the solar panels a little bit.
Yeah, it's a good point. Or make them track the sun, maybe.
Carol, you mentioned about the Virga snow on Sol 99. And you said, I think you made a comment that you saw it falling down, and then you see white on the surface. So my question to you is, how did they determine that this was not just occurred to be the CO2 frost like you see in the polygonal areas, and that it would be water ice, the Virga?
Yeah.
Or is this just an assumption?
It's the time of year.
It's the time of year.
So
Thank you.
basically, CO2 ice is not going to form at those temperatures that are, summertime temperatures. If it were winter, that's absolutely what you think it is, the CO2 snow.
Hey, Carol, what's the mechanism whereby the ice gets underneath the soil? You see soil covering up ice.
Well,
so how did the ice get under the soil?
That is the $800 million question. So I proposed one mechanism that the ice could get underneath the soil, which is the frost wedge or the ice wedge polygons. Mm-hmm. There are other mechanisms where segregated ices form as a result of freeze-thaw processes. And they don't form just in cracks, they actually form in layers. Another possible process that has been suggested is if there is enough snow on the ground, that wind blowing the snow could actually result in snow accumulating in a crack, in a trough area, and then subsequently it getting covered up by soil. But the fact of the matter is that the ice is not stable sitting at the surface. It's only stable under a few centimeters of soil. So you have to not only get it there, but you have to cover it up with soil. And in order for it to survive over essentially geologic time. The other thing is that if you have just dry soil at a depth of about 5 centimeters, the atmospheric vapor deposition will actually deposit ice into the soil, and that will sinter and become ice cemented soil. And we think that that's actually what we see in the polygon center, is we see ice cemented soil. That's why it's not white. It's been vapor deposited. And no one, expected to see white ice at the Phoenix landing site. Ice cemented soil was what was expected. And Mike Mellon, who was the team member of the mission, who was basically responsible for the modeling of the ice soil processes, predicted that we would see ice cemented soil at 5 centimeters depth, and we did. It's just this white ice that was unexpected. And to me, that's the big question, is what is depositing that ice, and is it involving a liquid process or not?
It can't be the remains of a large snowpack which has gradually shrunk down over time, and then all that soil that's on top is just what has remained out of the dusty snow. I mean, that seems that, the quantity of soil on top of the ice is enormous if you have to imagine it as being kind of dust incorporated in snow, and then that snow having sublimed away and left this thick layer of dust.
Right.
Somehow you have to think of some scenario whereby the water gets underneath the dust and then forms ice and lifts the whole thing up, like a kind of frost heave effect.
Well, that's what happens in periglacial terrain on Earth, but it happens at near the freezing point of water. In other words, these are processes that really are happening near 0 degrees centigrade. Not, drastically lower temperatures. And I think the important thing about Mars is that, at least in the subsurface, the temperatures are very low. They can get very high at, right at the surface, but you get down 5 centimeters and you're at the mean annual temperature, and that's like 220 Kelvin. So it's very, very cold. Mark.
I kind of remember this vaguely from the time, but why didn't you sample the ice, or did you try to, or it wasn't possible, or the white ice?
We didn't sample the ice. Well, I'm in an awkward position to explain this, because I was, every single day of the mission, advocating with all my, pushing with every bit of my strength to sample the white ice. and we just didn't do it. As I said, there were a couple of reasons. One was that the angle that the trough where that Dodo Goldilocks was sitting at was slightly off from horizontal. It was about a 14-degree slope, as I recall. And the RASP, which is the device we had for sampling ice, had to sit on a level surface. And so getting the RASP to dig into that stuff at that angle was thought to be difficult. No one tried it, but it was thought to be difficult. Another issue was that we were having great difficulty getting any samples at all to fall into the TIGA instrument. And that was because the samples were sticky, and they just didn't go through the screen. TIGA had a screen, and it also had a shaker, but the samples didn't go through the screen, and several of the samples didn't go in at all. And so another issue was that the mission had 160 days that it operated, and if we'd had 10 years or 2 years like a MER mission, we would have probably gotten around to it. It always was kind of on the agenda, but it wasn't a high priority on the agenda. And so that was kind of the reasons. That I seemed to be the only person on the science team who really cared about it, and I cared about it because of the habitability. To me, it was the most important sample to get. But other people had other priorities, and it just wasn't a team consensus that should be pushed to the front of the queue.
Okay, if there are no more questions, Carol, we have a small memento that, as I understand it, it's you can accept it because it's less than the federally mandated amount for gifts. And would you all join me in thanking Carol for her?